functionalities. So we'll see some of these models as well during the demonstration. At any point of time, if you have any queries on whatever we are presenting, and if you have any queries on the different research topics you have in mind, so please feel free to type them in the questions tab. And due to shortage of time or due to any other reason we are not able to take those questions up, I request you to send those queries to support@comsol.com, and one of our application engineers will get back to you. All right, so moving on. Yeah, so for modeling different kinds of electromagnetic devices, we have different kinds of interfaces available within the AC/DC module. Right? So if you're more interested in modeling capacity problems, the major phenomenon to be considered is the electric field of the system. Right? So we do not compute any currents in this particular which is the electrostatics interface, since the charge is large compared to the observation time, right? So which is unlike the electric currents interface. So where if you are more different kinds of cables as well, so you can incorporate interface. So this also supports different kinds of studies, right? So it could be stationary, it could be time dependent. If the effect is transient in nature, and of course multiple frequency domain studies are also supported. But in the case of electrostatics, so there is no distinction between different study types, right? So we are purely computing the electric fields in the system. So COMSOL also has the electric circuits interface, where you can model the external circuit of the electric charging and discharge using the different electrical lumped circuit elements, right? So these lumped circuit elements could be different resistors, inductors, capacitors. So it could be transistors and so on. And of course, you can couple these different lumped elements with the finite element model itself. So, for example, if you want to give the excitation for a transformer in the form of either excitation, current, or voltage, so that can be done through the coils interface by coupling the electric circuits with the finite element model of the transformer itself. And of course, you can import these electrical circuits in the form of SPICE netlist from any of the external software.
66,
and you can also
67.
export any of the electrical
58.
circuits that you have created within COMSOL to the external software as well.
58.
All right, so before we go ahead, so just to understand the kind of audience that you have for today's webinar, so I request you to answer this particular poll question, which you will be able to see on your screen just now. Please select the relevant and appropriate option for you. All right, so before we go ahead, just to understand the kind of audience that we have for today's webinar, so I request you to answer this particular question. Okay, so thank you for answering this particular poll question. All right, so coming back to the slides. So let us first start off with the power transmission equipments and how these equipments can be simulated within COMSOL. So whenever we talk about insulators and any kind, the common example here is the string type of insulators, right? So that basically suspend the transmission line, right? So for these, basically we make use of the electrostatics interface to compute the electric fields in the surrounding air domain and also on the surface of the insulators itself. Right? So here right? And you can also simulate the corona discharge prevention gear as well, right? So these prevention gears could be in the form of corona rings or grading rings, right? So by also making use of the optimization module of COMSOL, you can accurately predict the location of the placement of these corona rings and the grading rings, right? So the accurate placement of these rings will minimize the electric fields in the surrounding domains, right? So this will in return reduce the losses, basically the electromagnetic losses for your transmission system itself. And of course, by making use of our the latest module, so which is the electric discharge module, you can also simulate the ongoing corona discharge as well and its detrimental effects. Yeah, so typically whenever the electric field exceeds the limit, the ongoing corona discharge initiates, right? And this can be accurately simulated within COMSOL. So based upon the application that we discussed just now, so let me take this opportunity to introduce you to one of our customers, so which is the Power Engineers Incorporated. Right. So this is a company based out of US, and they basically work on the different electric transmission devices, right? So this is a case of high voltage DC insulators, right? So the engineers at the organization basically made use of multiphysics modeling to perform very detailed studies of corona discharge on the customer's proposed transmission hardware. Right, so typically corona discharge is affected by a combination of multiple parameters, right? So this could be electric field strength in the surrounding medium. So it could be the device geometry itself being the shape. So it could be the different atmospheric conditions in the surrounding region of the insulator, and it could also be the surface condition of the conductor as well, right? So in this case, the simulation was used to basically determine the electric field strength near the surface of the energized hardware, right? So this being the line end and the other end being the ground end, right? And to estimate the probability of corona discharge at location with very high electric fields. So in this case, the simulation basically gave the engineers an opportunity to iterate different designs before the actual testing, right? And this basically helped them cut down on the cost of testing and also the time involved in the high voltage testing. Typically, the high voltage testing equipments are very expensive, and basically by investing in some sort of simulations before actually performing maybe only a couple of iterations of actual testing, you can largely cut down on the cost and also the development times as well. All right, now coming to the power transmission devices. So modeling cables is very crucial, right? So power transmission cables are another important aspect of power transmission, and within railway industry as well. So this is very relevant. So the computational resources so at our disposal have recently they have increased exponentially, right? So I say this because if you refer to any of the published research materials on this matter, let us say in the past 10 years, so one cannot help but notice a strong correlation between the year of publishing of that particular research paper and the level of detail present in the 3D models. So because of easily available computational resource, the level of details so within the computational model has increased exponentially. So although the aspects that are supporting this, such as the advanced solver algorithms, so it could be sophisticated mesh configurations to build your finite element mesh, and even the sheer computational power have improved the situation over the years. The biggest performance shift is caused by the introduction of few of the computational electromagnetics features, right? So these features could be in the form of twisted periodicity, or it could be also the short twisted periodicity. So these are some of the basically features available to reduce your computational domain, right? So because typically the cables span for hundreds and thousands of kilometers if it is a submarine cable, right? So in those cases, we can't consider the entire domain of the cable, right? So that would be computationally very prohibitive. So in that case, so we need to come up with some sort of electromagnetic or numerical approximation features, right? So within COMSOL, we have these periodicity features that are available in the form of twisted period. So we'll see some of these features in the demonstration as well, and of course you can also straight away refer to them from the COMSOL website as well. All right. So before I switch over to the COMSOL software itself, so just a brief intro to this particular cable model. Right. So this basically features the magnetic fields interface of COMSOL and also the electromagnetic heating multiphysics coupling. Right. So like I mentioned in one of the previous slides as well. So different kinds of electromagnetic losses lead to temperature rise in our devices. Right. To accurately capture the thermal effects on the material properties is very important, and COMSOL provides different features such as the linearized resistivity option, so within the constitutive relation, to capture these effects very accurately. Right. So we have different kinds of coil features that you can basically make use of to build your simulation model, right? And of course, we also have different features available to model the active and passive conductors. All right, so let me quickly switch over to the COMSOL graphical user interface. Okay, yeah, so what you're seeing on screen is the graphical user interface of COMSOL Multiphysics, right? So I've already opened this particular subsea cable model that we have in our application library. Right. So COMSOL offers a very easy to use and understand user interface to set up your simulation model. Right. So what you see on the left here is a model builder. So model builder, as the name suggests, basically takes you through the simulation steps in a very methodical manner. Right. So it could be initially to set up some of the geometrical or simulation parameters. So it could also be assigning different materials to your geometry. And so when it comes to the geometric aspects as well, so COMSOL offers a lot of advanced functionality to set up or create your own geometry within COMSOL itself. And of course, if you are using any other third-party CAD package, so you can use that to create your geometry and import it into COMSOL environment. Right. So there are standard file formats that are supported for you to import your geometry. But in this particular case, the geometry has been created within the COMSOL environment itself. Right. So you can see the different geometric primitives in this case. And coming to the materials, so we are assigning different materials to the different domains, right? So since this is a case of a submarine cable, right? So similarly, you can set up the cable geometry for any of the railway applications as well. Right? Yeah, so in this case, you can see the different materials assigned to different domains, right? So the water on the top. So this is a subsea cable. The cable is basically buried underneath the seabed, right? So this is the water. So then we have the gravel that we are modeling in the surrounding domain of the cable. So now if I zoom in to this particular geometry, so you can see the cross section, the 2D cross section of the cable itself, right? So in the surrounding domains, we have the gravel, so where we are modeling the different material properties as well, which are homogenized. And then we have the different components of our power cable itself, right? So if I zoom in further, and if I click on different materials, you'll be able to see that the different domains get highlighted in blue color, right? So it could be polyethylene, so which is the surrounding protective layer. So polypropylene for the optical fiber protective sheets. So then we have semiconductor compound for the optic cables. So bitumen compound, so which is basically acting as a cladding. So then we have the silica glass itself for the optic fiber, stainless steel protective casing. So then we have copper domains, right? So which is the actual coil material which carries the electric current. So then we have the lead sheathing around the copper, so galvanized steel and so on, right? Yeah, so basically COMSOL also offers a material library, so which is very vast. So it consists of close to 14,000 different materials and corresponding material properties, right? So we basically collaborate with different material vendors and we obtain these material properties directly from those material vendors, right? Okay, so that is on the material aspect of it. So coming to the physics setup, so within COMSOL, we refer to the different boundary conditions, right? So when it comes to the simulation softwares, so we need to assign different boundary conditions, right, to set up our simulation model. So in COMSOL, we refer to these group of boundary conditions as physics interfaces. right? And yeah, so as the name suggests, the physics interfaces are basically grouped based on the domains that we are working with, right? So within the electromagnetic domain, we have different kinds of physics interfaces. So it could be the magnetic fields if you are basically working on the electric cable itself. So if we are working on, let us say, any sort of high voltage insulator, so we'll be basically working with the electrostatics physics interface, right? So if you are working on let us say heat transfer, where we want to see the temperature rise because of various electromagnetic losses. In that case, we'll be adding a heat transfer physics interface as well. So we'll be doing that particular step in this demonstration model itself. Okay, so just to set up this particular electromagnetic model, so as a default node, we have the free space, the magnetic insulation, and some initial values. So to set up the conductivity within these conducting domains, right? So let me quickly add the relevant boundary conditions. All right. So first thing is we need to define some sort of constitutive relation when it comes to the electromagnetics, right? For that, I'll right click on the magnetic fields, and you can see the different boundary conditions, domain conditions, and edge conditions, right? So for now, first I'll add the Ampere's law in solids. Basically, for all the conducting domains, we need to add this particular domain condition, right? And so basically, I've added the Ampere's law in solids, and I'll be selecting all the solid domains. All right, so here, so for the Ampere's law in solids, so this is the particular settings page, right? Here you can see that we need to define the different constitutive relations, right? So that define the relation between B and H, and also the relation, the conductivity relation, right? So the conduction model that defines the relation between J and E, right? So for B and H relation, you can also import the BH curve for that particular material and assign it here, right? So in this case, we are basically going with the relative permeability model. And of course, you have magnetization, remnant flux density, hysteresis, Giles-Atherton model, and so on. Right? Yeah, so for now, this is the constitutive relation that we have selected with regards to the BH relationship. Right? So coming to the conductivity model, so we are going with electric conductivity itself, where basically the software considers the electrical conductivity of different materials here, right? And of course, so if you want to consider the effect of temperature into your conduction model, you can go ahead with the linearized resistivity as well. Now, if I select that, you can see the equation, right? So which is a function of temperature here. All right, so for now, I'll switch back to electric conductivity. Yeah, so now we need to define the coils for the three current carrying conductors, right? For that, within COMSOL, we have the feature called the coil feature, right? So here I'll add the coil feature here, right? And I'll select basically one of the cores here, right? So I've selected this. And now we need to select the conductor model, right? So within COMSOL, we have either single conductor or homogenized conductor, homogenized multi-turn conductor, so which we'll explore in the further slides. And we also have the homogenized Litz coil if you are interested in modeling the Litz coil here, right? And the coil excitation could be in the form of voltage, current. You could also, basically combine the electric circuits with the FEM model. Like I was mentioning in one of the earlier slides, you can combine your finite element model with the electric circuits, right? So in that case, you could get the voltage or the current from the circuit itself. So for now, we'll be going ahead with the current itself, and I'll basically give this particular current as I naught. Right. So because I've already defined a parameter called I naught, which is equal to 926 amperes, right? So this particular parameter has been, basically defined under the electromagnetic properties, right? So you could see the I naught parameter here, which is equal to 655 square root of 2, right? So basically the rated current in this case, right? So we have the other simulation parameters as well. So it could be the frequency, angular frequency, phase to ground voltage, relative permeability of different materials, the skin depth of different materials, and so on. So similarly, it could also be the different geometric parameters as well, right? So the cross-sectional data, the relative length of cross-bonded data, total length of the submarine cable, and so on. And also, it could be very basic properties as well, such as the diameter of the main conductor coil here, right? So that you see. So the insulation thickness of different materials, the lead sheet thickness, and so on. So all of these can be parameterized, and at a later point of time, if you want to run any sort of parametric optimization studies, right? So you could basically use these parameters for performing those optimizations. Yeah, so I can also use the linear to linearize resistivity, and you can see it is rho naught into 1 plus alpha delta t, right? So this t will come from the heat transfer interface that I'll add in a moment. Right? So now I'll have to add coil features for all the three coils, right? So this is a three-phase coil. So I'll add another coil here, or I can simply duplicate this particular coil. So I've added another coil here. So since this is a three-phase conductor, so I need to define the phase difference between the first and the second coil, right? So within the coil current. So I already have the particular expression for that. So I'll just copy it here. Right. So here the phase difference between the first and the second coil is 120 degrees. Right. So I'll basically duplicate this particular coil again, and I'll change this to 240. Right. So basically 120-degree phase difference between the currents in the three coils. Right. So now we have defined the coils, the three coils for the three-phase conductors. Right. Okay. So for the first coil, it was so basically this domain. Okay. So for the first coil, I'll select maybe this domain, and for the second coil, this particular domain. And for coil 3, we have this, right? Okay, so now we'll also have to define the Ampere's law in other conductors as well, because basically we want to see the different losses due to eddy current and other inductive losses, right? So within the other conductors as well. So these conductors being the screens and the cable armor, right? So for that, I'll right click on magnetic fields and add another Ampere's law in solids. So here maybe I have already created different geometric selections based upon the different components within the cable, right? So for now, I'll select armor and screens, right? Okay, so you can see the blue domains here, right? So these are basically the armor domains, and these are the screen domains. All right, so now we have defined the constitutive relations in these domains as well. Now, our main objective, apart from performing the electromagnetic analysis, is to perform thermal analysis as well, right? So, because we want to see the temperature rise because of different hysteresis and eddy current losses. Right? So, I'll add that particular physics interface here. So, basically, on the top, what you see here is the different tabs for accessing the different aspects of the simulation model, right? So, I'll basically go to the physics here. So the same options to add the material can also be accessed from the top tabs as well, right? So if you want to add any materials here, you can click on materials tab and click on add material, right? So here you will be able to see the different materials basically categorized based on the physics itself. So under AC/DC materials, so we have different kinds of magnetic materials from our suppliers. So different hard magnetic materials, copper, aluminium, soft iron without losses, with losses, and so on. Yeah, so this is on the material model itself. So coming back to the physics, so now I'm interested in knowing the temperature rise, right? So for that, I need to add the relevant physics. So I'll click on add physics, and now I'll go to the heat transfer. Right? So here once again, So it could be solids or any kinds of fluids, right? So in our case, it is mostly solids if we consider only the gravel domain. So I'll click on heat transfer in solids and I'll click on add to component 1. So now you can see that heat transfer in solids physics interface has been added under component 1. So I'll close this particular section. Okay. All right. So yeah, now that we have added the heat transfer in solids node, so I'll just give one boundary condition. So just to constrain the temperatures, right? So I'll right click on heat transfer in solids, and so we have once again different conditions here, right? So if you have a fluid as well, so you can add the fluid and assign the relevant domains there, right? So if you have any heat source or within, if you have any specific media, right? It could be porous media, different kinds of biological tissues, building material, shape memory alloys. So all of these can be modeled within COMSOL. So for now, I'll just constrain the external boundaries of our domain with a particular temperature, right? So I'll go to the temperature and maybe select all the external boundaries, right? And I'll constrain it to the ambient temperature being 293.15 Kelvin, right? So this will be the basic thermal setup that I'll do for now. And of course, I need to, basically add the multiphysics coupling here. So within COMSOL, based on the physics interfaces you have added to your component, right? So COMSOL will automatically suggest the relevant multiphysics coupling. So it could be electromagnetic heating, right? So this electromagnetic heating could be because of Joule heating. So it could be because of induction heating, right? So it could be because of RF heating and so on. So thermoelectric effect is also a multiphysics phenomena between the magnetic fields and heat transfer. And similarly, we have other electromagnetic interfaces as well, right? So for now, I'll add electromagnetic heating physics interface. And here in the settings, you can see that the coupled interfaces are basically the magnetic fields and the heat transfer in solids. Right? So this is the basic simulation setup. And coming to the mesh, so COMSOL offers advanced meshing functionalities. So for a very beginner user, so COMSOL offers what we refer to as the physics controlled mesh. So software will based upon the physics interfaces that are involved, right? So in this case, being the magnetic fields, heat transfer, and electromagnetic heating. So based upon the inputs of the different boundary conditions within these physics interfaces, COMSOL meshing algorithm will automatically create a mesh, right? So you don't have to think a lot to create the mesh in this case. But of course, if you are a more mature user, in that case, you can switch over to user controlled mesh. So there you'll be basically seeing the different advanced user defined options to further modify your mesh, right? It could be triangular mesh, quad mesh, so it could be, when it comes to 3D, it could be tetrahedral mesh, or it could be a cube mesh, and so on. And of course, there are other modifying operations and booleans and partition operations within the meshes and so on. Right? So this is on the meshing side. And yeah, so when it comes to the study itself, so based upon the physics, once again, COMSOL offers different kinds of study types. Right now, if I right click on the study, so you'll be able to see the different kinds of study types that are available. Right. So if I go to the study tab at the top, now you can see all the study types that are supported, right? It could be a basic stationary study, or it could be a time dependent study. So it could be a frequency stationary, or frequency time periodic, and so on, right? So depending upon the kind of application you have, for example, if it is more of AC devices, so we'll be going ahead with frequency domain study, right? For any sorts of DC applications, it is mostly going to be stationary study or a time dependent study, right? And if you want to see the transient behavior within any AC machines, right? So then you can basically go ahead with the frequency time dependent study, right? So there are such hybrid kinds of study types that are also supported within COMSOL, right? So for now, we have right. So that is the reason we have gone ahead with the frequency stationary study. And if you see the physics that we are solving for, right? So basically the magnetic fields, it is being solved in the frequency domain, right? The frequency being 50 hertz. And once the electromagnetic computation is done, we are basically solving for the heat transfer in the stationary domain, right? So we are going to see only the steady state temperature values, right? Yeah. So this is on the study type. So now if I click on compute, so it will probably take a few seconds since this is basically a 2D model. So keeping in mind the time constraints that we have, I already have a solid model with me. Right? So let me just open it up. Yeah, so this is the solid model that we have. And after the studies, you can see the results and visualization section, right? So this is basically the post-processing step. Now, if I click on magnetic flux and zoom in, yeah, you'll be able to see in this case. You can see the magnetic flux distribution as well, right? So here you can see capacity values as well, right? So the maximum current. Let me now switch back to the slides. All right, so based upon this particular demonstration and the capabilities for cable modeling, so yeah, so we can see the graphic that you see, right? And the pink line that you see here is that of the where you don't have to model kilometers of length of your particular cable, right? So using this twisted periodicity feature, you can reduce your computational domain from kilometers to maybe a few meters, right? So that is the kind of functionality that COMSOL provides when it comes to the cable modeling itself. So based upon these features, let us now look at another case study from one of our customers. So this is from Hellenic Cables, right? So they basically work on subsea cables for offshore wind farms. The team of engineers in this particular case study used finite element modeling to study the inductive and capacitive coupling and the resulting thermal effects due to various losses. So they also considered the thermal resistance of the surrounding soil as well, right? And also the grounding resistance. The surrounding medium that is around the cable also provides certain thermal and electrical resistances, right? So they've also considered the effect of these resistances as well into their simulation model. Yeah, so this is one case study that I wanted to highlight. So whenever we think of modeling any cables, so we need to model the coils, right? So basically the current carrying conductors are modeled as coils within COMSOL. And so now let us look at some of the features that are available to model these conductors. Right? Now in this case, so we have three different cases, right? In all these three cases, it is carrying the same amount of copper that we have used to basically construct these cables. It also carries the same current, right? So which obviously means that it is same DC resistance. But if you look at the configuration, basically the geometry configuration, and if you also consider the frequency of the electrical current, the losses are not going to be the same. Right? So this is basically because of what we refer to as the skin effect when it comes to alternating current. So in the first case, in the first and second cases, the frequency is 50 hertz. Right? At 50 hertz, if you consider the configuration where the radius of the coil or the strand is much larger than the skin depth. Right? So what you see here in the orange color is basically the skin depth because of this particular frequency. So basically the skin depth is a function of frequency, right? Apart from other factors. So here the size of the coil itself, or the size of the coil, is basically twice the skin depth, right? In this case, for using the same geometry, we can use the single conductor model that is available within COMSOL. So earlier during the demonstration, I showcased the three different models that are available to model our coils, right? So it is the single conductor coil, the homogenized multi-turn conductor, and also the Litz coils, right? So in this case, in this particular case, where it is 50 hertz, and so basically the skin depth is very low compared to the size of the coil itself. So we can use the same geometry, but we can use a single conductor coil, right? And if we consider another case where the frequency is still 50 hertz, but in this case we are basically modeling multiple strands within the coil, right? So here the radius of the individual strand is much smaller than the skin depth. So in this case we can essentially simplify the geometry and use the homogenized multi-turn conductor. Right. So here, as you can see, the size or the radius of the individual strand is much smaller than the skin depth itself. Right. In this case, the AC resistance is almost equal to the DC resistance. Right. So in this case, you can basically make use of the homogeneous multi-turn conductor model. By choosing this, you are basically simplifying the geometry. Right. So you don't have to use all of these individual strands explicitly. You don't have to model these strands explicitly. So you can consider one homogenized cross section itself, that is equal to the sum of the cross section of all the individual strands, right? But so at very high frequencies, so let us say in this case close to 500 hertz, where the skin depth is much smaller than the size of the conductor, right? So the inductive effects also needs to be modeled, and for that you can either use a single conductor model or use the RLC group coil feature that is available within COMSOL, right? So here you can basically see the inductive effects, right, and also the skin depth effect. Right. So so for those of you interested, I encourage you to basically visit the COMSOL website and download these models that are available. Right. And if you want to discuss further on any of the technical aspects of these models, so please feel free to write to support@comsol.com. Yeah. So this is on the different features that are available to model the current carrying conductors within COMSOL. Yeah, and not just those conventional coils, but you can also model what we refer to as the Litz wires, right? So these Litz wires are basically used in devices that require very high frequency AC. Right? So process due to skin and proximity effects. Right, so they are commonly found in many of the power electronics applications. So it could be transformers, for example, within the power electronics domain. Right. Yeah, like I was saying, it is used in high frequency transformers, in power converters for electric trains, in the context of railway industries, and also methods available to model these. Right, so homogeneous multi-turn setting, you can set the number of turns to 1. equal to the sum of all the strands, the sum of the cross section. Right. So this is the functionality for modeling the Litz coil. All right. So I would like to present another case study from one of our users here. Right. So in this case, the focus was mainly on the cable analysis. Right. So it was focused particularly on the heat transfer to help engineers analyze the different cable ratings. Right. So essentially, under different environments, such as underground tunnels, is what you see in the picture here, and also in the simulation results here. But not just that, it could also be in cases where the cables are directly buried underneath the soil. Right. In these setups, the close proximity between cables can essentially impede heat losses. Right. So it can also lead to a rise in the temperature of both cables and basically reduce the current carrying capacity of all the coils. So in this simulation image, what you see here is the results of a normalized airflow profile. So within the cross section of the tunnel here, right? So this is a case of both electromagnetics as well as CFD analysis, right? So because of electromagnetic losses, we are computing the temperature rise, and basically due to the temperature rise, what is going to be the flow of air within the tunnel, right? So we need to have the most efficient configuration that will lead to efficient distribution of temperature or thermal energy within the tunnel, right? So this is one such case of where engineers have used the multiphysics approach for modeling their case. All right. So based upon what you have seen in the slides and during the demonstration as well, so we would like to know your area of interest when it comes to modeling different cables and power electronic devices. I would be launching another poll question here. I request all the attendees to select the right responses here. So if you are interested in modeling components of power electronics devices, or more towards the thermal aspect of it, so which is being the electromagnetic heating effects of power electronic devices, or if you want to know the thermostructural effects of power electronic devices, right? And if you're working on any other field, please feel free to type them as well. We'll probably take 10 seconds for everybody to respond. Okay, thanks everyone for answering that poll question. All right, so until now we saw the different aspects of the power transmission. So this being any sorts of insulator design or even the cable design, right? So both of these are very so where you don't have model kilometers of length of your particular cable, right? So using this twisted periodicity feature, you can reduce your computational domain from kilometers to maybe a few meters, right? So that is the kind of functionality that COMSOL provides when it comes to the cable modeling itself. So based upon these features, let us now look at another case study from one of our customers. So this is from Hellenic Cables, right? So they basically work on subsea cables for offshore wind farms. The team of engineers in this particular case study used finite element modeling to study the inductive and capacitive coupling and the resulting thermal effects due to various losses. So they also considered the thermal resistance of the surrounding soil as well. right? And also the grounding resistance. The surrounding medium that is around the cable also provides certain thermal and electrical resistances, right? So they've also considered the effect of these resistances as well into their simulation model. Yeah, so this is one case study that I wanted to highlight. So whenever we think of modeling any cables, so we need to model the coils, right? So basically the current carrying conductors are modeled as coils within COMSOL. And so now let us look at some of the features that are available to model these conductors. Right? Now in this case, so we have three different cases, right? In all these three cases, it is carrying the same amount of copper that we have used to basically construct these cables. It also carries the same current, right? So which obviously means that it is same DC resistance. But if you look at the configuration, basically the geometry configuration, and if you also consider the frequency of the electrical current, the losses are not going to be the same, right? So this is basically because of what we refer to as the skin effect when it comes to alternating current. So in the first case, in the first and second cases, the frequency is 50 hertz, right? At 50 hertz, if you consider the configuration where the radius of the coil or the strand is much larger than the skin depth, right? So what you see here in the orange color is basically the skin depth because of this particular frequency. So basically the skin depth is a function of frequency, right? Apart from other factors. So here the size of the coil itself, or the size of the coil, is basically twice the skin depth, right? In this case, for using the same geometry, we can use the single conductor model that is available within COMSOL. So earlier during the demonstration, I showcased the three different models that are available to model our coils, right? So it is the single conductor coil, the homogenized multi-turn conductor, and also the Litz coils, right? So in this case, in this particular case, where it is 50 hertz, and so basically the skin depth is very low compared to the size of the coil itself. So we can use the same geometry, but we can use a single conductor coil, right? And if we consider another case where the frequency is still 50 hertz, but in this case we are basically modeling multiple strands within the coil, right? So here the radius of the individual strand is much smaller than the skin depth. So in this case we can essentially simplify the geometry and use the homogenized multi-turn conductor. Right. So here, as you can see, the size or the radius of the individual strand is much smaller than the skin depth itself. Right. In this case, the AC resistance is almost equal to the DC resistance. Right. So in this case, you can basically make use of the homogeneous multi-turn conductor model. By choosing this, you are basically simplifying the geometry. Right. So you don't have to use all of these individual strands explicitly. You don't have to model these strands explicitly. So you can consider one homogenized cross section itself that is equal to the sum of the cross section of all the individual strands, right? But so at very high frequencies, so let us say in this case close to 500 hertz, where the skin depth is much smaller than the size of the conductor, right? So the inductive effects also needs to be modeled, and for that you can either use a single conductor model or use the RLC group coil feature that is available within COMSOL. Right, so here you can basically see the inductive effects, right, and also the skin depth effect. Right, so yeah, so for those of you interested, I encourage you to basically visit the COMSOL website and download these models that are available, right? And if you want to discuss further on any of the technical aspects of these models, so please feel free to write to support@comsol.com. Yeah, so this is on the different features that are available to model the current carrying conductors within COMSOL. Yeah, and not just those conventional coils, but you can also model what we refer to as the Litz wires, right? So these Litz wires are basically used in devices that require very high frequency AC, right? So while minimizing the power losses, basically this Litz cable configuration is used if you want to minimize the power losses due to skin and proximity effects, right? So they are commonly found in many of the power electronics applications. So it could be transformers, for example, within the power electronics domain, right? Yeah, like I was saying, it is used in high frequency transformers, in power converters for electric trains, in the context of railway industries, and also in the inverter circuits used within the traction motor controls, right? And once again, in COMSOL, you have the different methods available to model these, right? So homogeneous multi-turn setting, you can set the number of turns to 1 if you want to model the Litz wire, but set the area of cross section which is equal to the sum of all the strands, the sum of the cross section of all the strands, right? So this is the functionality for modeling the Litz coil. All right, so this slide is more on the multiphysics aspect of power electronics device itself, right? So as you might already know, you can start off with electromagnetic analysis, and then because of the various electromagnetic losses, so that lead to temperature rise, right? So you can couple the electromagnetic interfaces with the heat transfer interface. And if you're interested in modeling any of the cooling systems, right, so basically thermal management for your power electronics devices, you can perform conjugate heat transfer simulations by coupling it with CFD, right? And if you want to perform any kind of thermostat simulations, right, so basically thermal expansion, so and so on, so you can couple the electromagnetic interface with solid mechanics interface. So the forces can come from either different electromagnetic forces or magnetostriction effects, and you can compute the deformations due to these effects. And if you're interested in knowing any of the acoustic parameters as well, right? So like I mentioned in one of the earlier slides, so because of these high frequency AC, so this could lead to magnetostrictive effects, so which could in turn lead to vibrations as well, right? So here you can couple the solid mechanics with acoustic interfaces. So this is the kind of multiphysical analysis you can perform within COMSOL. So coming to another case study, so ABB Semiconductors have been using COMSOL for performing multiphysics simulations. In this case, it is for the insulated gate bipolar transistor modules, right? So objective was to understand the engineers were able to extend the life of the IGBT modules by a factor of 4 for the stitch bonded layout and by a factor of 10 for the reinforced emitter contacts, right? So so this is the kind of advantage they gained by basically performing simulations. So you can specify the excitation. So the settings is basically asking me to select the particular boundary where I want to give the terminal, right? So now I'll select this particular boundary for the excitation, right? And I'll give the input current. Yeah, input current as IC here. Yeah, so this is the input current that we have, once again parameterized, right? So in this case, the value of IC is 166.67 amperes that I've already defined as a parameter here, right? So then I need to give a particular ground as well. So for that, I'll select this particular boundary here. Right. So we have the terminal and we have the ground. Right. And within the electric currents interface, we are solving for these domains. Right. So now I'm interested in knowing the electromagnetic heating. So once again, I'll add the relevant physics interface here. So I'll go to add physics, and then under heat transfer, I'll add heat transfer in solids. Right. I'll add this to the component one. Okay, and close this particular window. Okay, so within the heat transfer in solids, I need to give certain boundary conditions, right? So I need to give a certain heat flux so that the heat is constantly removed from this particular device, right? So the value of this heat flux can come from multiple sources, right? So it could be either active cooling where you are modeling any sort of liquid cooling. It could also be cooling because of some passive sources as well, such as heat sinks and so on. For now, we are not accurately modeling the CFD aspects of it here. So we are only implicitly modeling the heat removal, right? So for that, I'll right click on heat transfer in solids and add a heat flux boundary condition, right, on the bottom of the face, so where the heat is being removed, right? So for that, the flux type is basically convective heat flux, and the heat transfer coefficient is in the form of a parameter called Hc. Right, so it is 650 watts per meter square Kelvin, and the external temperature is basically in the form of this parameter, which is TEXT. The ambient temperature is 318 Kelvin, right, close to 55 degrees or 45 degrees. All right, so this is the basic boundary conditions for the heat transfer in solids, and of course I need to add the electromagnetic heating as well, that couples the electric currents and the heat transfer in solids, right? Okay, so we have the mesh as well, right? So in this case, it is a user control mesh. You can see that there are fine elements in some of the domains of the wires here, and overall it is a fairly conservative mesh, right? So this is going to be a stationary study, right, where I'll be solving for electric currents, heat transfer, and electromagnetic heating. So keeping in mind the time constraints, I would like to once again open the solid model. Okay, so this is the solid model, and so if we go to the results and visualization part, so what we are seeing here in the graphics is the electric potential distribution, right? And now we can also see the current density across the different components of the IGBT, right? So we can see that the current density is really high, close to 15 e power 7 amps per meter square, right? In some of the wires here, so which is really high. It can lead to temperature hotspots, right? And I can also plot the volumetric loss density as well, right? So because of the Joule heating and the resistive effects, and of course I can also plot the temperature rise because of these electromagnetic losses, right? So it is fairly high here, close to 93 degrees Celsius, right? Okay, so this was actually for this particular wire bonding configuration, right? So let me switch back to the earlier model, right? So, and if I go to the parameters here or the geometry here, so under geometry I have the option to program it as well, right? So based upon the parameter value. So in this case, I want to model some additional wires. So if you focus on this area, so right now the number of wires here is fairly less compared to what you're about to see now, right? So I'll change this parameter to 1. So I want to increase the number of wires, and I'll go to geometry and build all. Right now you can see that there were a few additional wires that were added. So now let us see what is going to be the change in our particular configuration. So we'll be solving the same model setup, same electric currents and heat transfer. So I already have the solid model for this particular case as well. right, for the additional wires. I'll just showcase those results. Right. So now if you see the current density normal, so now it is close to 13 e-power 7 compared to earlier value of 15 e-power 7, right? So the current densities have dropped by a considerable amount by increasing the number of wires, right? And of course the loss density as well. Now if we look at the overall temperature rise because of the resistive heating, it has come down to 87 degrees Celsius compared to the earlier 93 degrees Celsius, right? So you can perform these kinds of parameterization or parametric studies and even parameter optimization studies as well. Right. All right. So so this is what I had to present on. Back to the slides. Okay, so in conclusion, I would like to say that COMSOL as a simulation package, basically offers advanced functionalities for modeling, single physics phenomena as well, right? So if you're interested mostly in electromagnetic modeling, so that is also possible. For it could be for cables, power electronics devices, to model the capacitive effects or resistive effect and so on. So in addition to these single physics phenomena, you can also couple the other element of physics phenomena as well, right? So in this case it could be the heat transfer coupled to electromagnetics. So it could be so it could be structural effects coupled to electromagnetics and acoustics and so on, right? So COMSOL also offers unique and advanced functionalities to perform such multiphysics analysis as well for the different applications for the railway industries. All right, so I would like to launch the last poll question for this webinar. I request all the audience members to kindly select the appropriate response. So once you are done with answering this particular poll question, I would also request you to type in your any of the questions that you might have. So based on what you have seen until now, right? So the slides and as well as the demonstration models. And of course, if you have any additional topics that you would like to discuss, please feel free to email to support@comsol.com. So we would be glad to get back to you.